Okay, so here, net ionic equations. This begins going back over reactions, back over balancing. As you can see, it's a nice graphic here of balancing equations. But we're also going to get in specifically to net ionic, which means precipitation reactions, solubility rules, and other things like that. So, enduring understanding is the same as the other Unit 4 ones. Basically, we're looking at chemical change, different substance, and this can be represented by chemical equations. Specifically for this set of notes, we're going to write balanced chemical equations for physical changes, and we're going to do it for given information about identity of reactants or products and for ions. So that means we're going to get into those precipitation reactions, separating them into ions and things. So that's why you probably notice at the end of your packet, you see lots of the polyatomic ion charts and other things for naming, so you can refresh that. That's the only real way that you know how to break them up into their ions from the chemical formulas, if you know their charges and things like that. The essential knowledge here goes a little bit more in specific of what I was just talking about. You're going to do solubility rules, break them into ions, you're going to balance, you're going to do all that. This essential knowledge specifics are in the course exam and description if you want to look at that on AP Classroom. All right, so balanced equations. All physical and chemical processes can be represented symbolically by balanced equations. Chemical equations represent chemical changes, showing the rearrangements of atoms into new substances. Which brings us to the graphic below, as you can see, which is the combustion of methane, or natural gas. You have one molecule of methane, CH4, that's combining with 2 molecules of oxygen. Significant part here, showing your reactants. But in the middle here, this section, we're showing all of the atoms have been separated. That means that bonds have been broken. Okay, bonds are breaking. And over here, we're creating 1 molecule of carbon dioxide, 2 molecules of water vapor. So as you can see that we have the formation of new bonds in the product. So this is new substance. This is definitely chemical change here. Now, the law of conservation of mass, of course, is the reason why balancing is done. You cannot create or destroy matter. It is not created nor destroyed. It is just altered, bonds breaking, bonds forming, sometimes not even altered in terms of the chemical composition. If we're talking about a phase change, you're just going from the solid form to liquid or liquid to gas. However, chemical equations must contain equal numbers of atoms of the element before and after the change occurred. This specific example in here is a very good graphic of a chemical equation. We have 2 of the sodium hydroxides, and it's aqueous, meaning it's dissolved in water. It's a solution. It's represented by the gray part here in the diagram. Technically, though, sodium hydroxide is a clear solution. It's a base. It is being reacted with the copper sulfate solution, which is the blue solution. Remember, most copper solutions are blue in appearance. Now, the other thing to note in this graphic is showing you the balance beforehand, 67.25 grams of your reactants there. Over here in the products, it's going to make sodium sulfate and copper 2 hydroxide. This is a solid though, so that means it's going to precipitate out. So over here, trying to show you that some of it's precipitating out, and it's a blue substance. That's why I made the chemical formula blue here. Copper 2 hydroxide is a light blue powdery stuff that falls to the bottom. Noticing here in the products, it's the same number of grams. So if you start with that number of grams of stuff, you should end with that number of grams of stuff. That means the mass is conserved, but also the same number of atoms is being conserved as well. This is really just review. Remember, the reactants are on the left of the arrow, the products are on the right. The arrow means yield or produces. Coefficients are the large numbers in front of the molecules, elements, or compounds, depending on what we're looking at here. Subscripts are the number of atoms in the molecule or compound. And then, of course, we use the states of matter symbols next to our elements and compounds to show what phase of matter it's in. The only one that you might need a refresher on, I'm pretty sure, is AQ. Means it's dissolved in water. That means this is a solution. We've got a solution there. AQ means it is homogeneous mixture, solution, okay? Solid, of course, is S, liquid L, G is gas, very simply put there. And this graphic does a good job of showing, we have our coefficients here, 6, carbon dioxide, 6, water, forming 1 glucose, because it's understood 1 if there isn't a number in front of it, and then 6 oxygen molecules. So, this is actually the equation for photosynthesis. Carbon dioxide plus water gives you glucose and oxygen. Kind of representing all of those factors there for you, remembering how to read chemical equations. Now, the only thing we're allowed to manipulate in a chemical equation is the coefficients. You're not allowed to change subscripts. The only thing you can do is change coefficients to make sure the number of atoms balance on each side. So we have 2 showing that up here. The aluminum plus sulfuric acid example up at the top here. 2 aluminum atoms plus 3 of the sulfuric acids give you 1 of the aluminum sulfates and 3 of the hydrogen gases. Now, as you can see, and I'm going to go over this strategy in just a minute, but because sulfate is found on both sides of the equation, we keep the polyatomic ions together and balance it as a group, as shown above. So aluminum and then the hydrogen and then the sulfate were balanced accordingly. The next example down here, also showing you the ball and stick models as well. We have propane, C3H8, propane found in gas grills, big tank. With oxygen gives you carbon dioxide and water, but I like to show you here how they put it on the balancing scales here. You start with 3 carbon atoms, that means there's 3 carbon atoms in the products over there. We have 8 hydrogens, so 8 hydrogens in the products. You have 10 oxygens to begin with because of the 5 times the 2. That means you have 10 in the product. You'd have to add the 3 times the 2 is 6. The 4 times the 1, that gives you 10 total. So it does balance out. So now we're just going to recall some strategies for balancing and look at some chemical reaction basic concept design of types of reactions. So here are types of reactions. I put it in one big graphic for you. Synthesis, you take 2 elements, put it together to make a compound. Decomposition, you're taking one thing and splitting it apart. Now, single and double displacements, also you could call them replacement. I believe that's how we teach it in Chem 1. They're called replacements. But if you see this in the textbook or online, you'll see it either said as replacement or displacement, but they mean the same thing. Now, complete combustion, you know, as the organic plus oxygen gives you carbon dioxide and water. That one's pretty standard. Incomplete, you might not have seen. The really only difference is that you run out of oxygen, so you start producing some carbon monoxide as a byproduct. One other specific thing I want to address with double replacement or double displacement. There is a subset under it, neutralization. Does anybody remember what happens in neutralization? Yes?
An acid and a base combines to produce water and an ion, like a compound, an ionic.
Good. It gives you water and a salt. And salts are ionic compounds, so that's exactly stated correctly. This falls under the double one. It's a specialized one, and it has a specialized technique for balancing that makes it easier, which I'm going to show you. Now, do remember, too, that the reactivity series or activity series here, in order for single replacement to occur, the element has to be higher up on the activity series than the one in the compound in order to switch places with it. Has to be more reactive in order to kick the other one out of the compound. So activity series, and then of course, you do have two different ones that can switch. You can do cations or anions. If you're doing anions, that's going to be your nonmetals. Fluorine is the most reactive nonmetal. So fluorine can kick anything out of the compound, but it has to be higher up on the reactivity series in order for it to take the place of the element in the compound. Now double displacement, that's going to be, those are all compounds, whereas single is an element plus a compound, giving you an element plus a compound. Double is all compounds. Now, whether or not a double replacement reaction causes a precipitation to occur, that's going to be based off of the solubility rules, which we'll talk about later on in this set of lecture notes. So a couple little things to review there. And really, you know, we're going to be sticking more with, in terms of this unit, looking at aqueous solution reactions. So that's going to be precipitation, double replacement, acid-base, and redox stuff. Oxidation reduction reactions. All right, so let's talk about balancing strategies. Maybe you're not a little rusty on balancing, but first strategy, you have a reaction like this. The potassium chlorate solid is decomposing into potassium chloride solid and oxygen gas. This one particularly has an odd number in it, okay? So odd numbers are more of an issue to balance. You need to get rid of them. But if you need to start off this way, but by no means do you have to show this, because it's expected that you can balance in your head now, but you can still use the tic-tac-toe board as a tool. So I'm just going to show it and break it up into its elements. We have potassium, we have chlorine, and we have oxygen elements in this particular reaction. On the left, I count up the reactants. So I have 1 potassium, 1 chlorine, 3 oxygens. On the right, I have 1 potassium, 1 chlorine, and 2 oxygens. As you can see, the oxygens are out of balance, and a 3-2 combo is not going to work. So we need to go with least common multiple here. So what would be a least common multiple between 3 and 2?
6.
6. So what do we put here in order to balance?
6.
We put a 3, 3 times 2, that gives me 6 there. What do I put here in order to balance?
2.
A 2. Now, that fixes my oxygens, but it also changes my potassiums and my chlorines. So this goes to 2, this goes to 2. However, what you'll notice, it's an easy fix on the other side. Usually works itself out very nicely. So what do we put here? A 2. And that fixes everything, and now we're good to go. So that's the oddball ones. What strategy for that? Now, as you can see, down here is a neutralization reaction. We have potassium hydroxide plus hydrochloric acid, giving us calcium chloride and water. So this is a situation where I would tell you to do the HOH. So basically, when you see neutralization, you know that this is a base, this is the acid, and you know you see water over here, neutralization is occurring. Change your water to HOH. And let me show you why, because then you can pair up the OH group with the OH group and balance them together. You can take the H and balance it with the H over here. Makes it so much easier to see, and it's faster than trying to count the individual atoms. So if you turn water into HOH, which is fine, balance the H's together, balance the OH's together. So what's out of balance here? Cl's out of balance. Let's fix Cl. What do I put here to fix Cl?
2.
Put a 2 here. That fixes my Cls. Now, I have 2 hydrogens and I have 2 hydroxides because I have the 2 here and I have the 2 here. That's an easy fix. What do I put here?
2.
2. Now, would you have seen that if you didn't change it to HOH? Might not have seen that. We have 2 hydrogens and we have 2 hydroxides, and it balances very easy there. So it's just a way of speeding it up. If you see neutralization, I suggest that you use the HOH method. Now for organic combustion. There is an easy strategy for this if you can remember. Definitely will speed up balancing organic combustions. It's called the CHO. You must balance C first, then H, and then O at the very end. So let's go ahead, show how this works, and it never fails. It never fails on you. So, on the left, I have 6 carbons, I have 6 hydrogens, I have 2 oxygens. 1 carbon, 2 hydrogens, 2 plus the 1 here gives me 3 oxygens. Now, if I'm doing this strategy, I balance carbon first. So here, I'm going to put in front of carbon, what do I need? 6. I put that there, I change that to 6, got it, 6, the carbons are balanced. Then I balance hydrogen. What do I need to put there to balance hydrogen? 3 goes here, now that is also 6. Now I look to the oxygens on my products side over here. I have 6 times 2, so that's 12, not 8, excuse me, 12. Plus 3 times the 1 here, so that's 3. That gives me a total of 15 oxygen. So that's 15. What you should notice is we have 15 in our products, and we have the standalone oxygens by himself over here, which is O2. So O2, okay, I'm going to multiply that by 2 somewhere over here because of the 2 here. Now I take the 15, I divide it by 2, I get 7.5. Everybody follow me there? So I put the 7.5 here just temporarily for a moment, because we're not supposed to leave it as, decimal numbers. So like before, even when we're doing empirical formulas, when we got a decimal number, we multiplied through to fix it. So you just multiply everything by 2, put a 2 here, this becomes 15, this becomes 12, this becomes 6. Now, not every single combustion is going to result in a 0.5. Some of them will be 0.5, some of them will be whole numbers. If it's a whole number, you just stick it in front of the O2. If it's a 0.5, multiply through by 2, and then you're done. All right? So yay, we did that right. Last but not least, polyatomic ions. Like I said, on the back of your packet, I put a couple charts of polyatomic ions to help you refresh on some of them. So, we have zinc nitrate plus sodium phosphate, giving us zinc phosphate plus sodium nitrate. And we have 2 polyatomics here. We have the NO3, which is nitrate. We have PO4, which is phosphate here. So, in this case, when you have them on both sides, like so, you need to keep them together as a group. Since we have nitrate here, we have nitrate here, we keep that as NO3, sodium, and then phosphate, PO4, because there's PO4 on both sides. So don't break those up into individual atoms, it takes too long. We have 1 zinc over here, we have 2 nitrates. We have 3 sodiums, and there's no parentheses around the phosphate, so that's an understood 1. If there were more phosphates, you'd have parentheses with a number outside it, like it does here for the nitrates, okay? On the product side, we have 3 zinc, we have 2 phosphates, we have 1 sodium, 1 nitrate. I usually just start with the, the main metal here, and we're going to start here with our zinc. What do we put here? 3. So that changes this to 3, makes my nitrates go to 6, because 3 times 2 here. All right, now the sodiums and the phosphates are out of balance, but you notice the sodiums are attached to the nitrates here, so I'm going to balance that last. I'm going to go for the phosphates now. So I have 1 here and I have 2 here. What can I put here to fix that? Put a 2 here. Okay, so that's a 2. That makes sodium 2 times 3, so that's a 6. See how it nicely works itself out? What do we put here? 6, and then we have everything in balance. Now you're going to practice. Give you about 5-10 minutes to do the examples there. I'm going to note that A is a little bit on the tough side, so you might want to do some trial and error on that. I would start low and then start upping your numbers as you go. All Alright. So, looking at the practice now. Had some time to do some of the practice problems. On the first one here, like I said, it's more of a trial and error. You can start with, looking here. Oh, I have 2 hydrogens. I definitely have a mess of oxygens going on here, so I'll start with the 2. Well, if I do 2 there, the hydrogens match, but that means I also have to put a 2 here for the chlorines. So then you count up your oxygens. Well, there's 6 on the reactant side, and over on the products now we have like 7. So that's not going to work. I start low and then I go higher. Okay, well, 2 didn't work. Let me try 3. Well, if I look here, and I put a 3 here, that's great. That's 6 for the oxygens, 7 for this oxygen, and then 2, that's 9. Then the oxygens match, but now I have 3 hydrogens that aren't going to balance with those 2. So that's not going to work. So I start again, and now I'm going 1 more up. I'm going to do 4. Well, 4, I can fix the hydrogens easily. Do that. I can also fix the chlorines here very easily. And then I just count on my oxygens and hope that they match. Well, 4 times 3, that's 12. So there's 12 there. And then 4 times 2, this is 8. Plus 2, plus 2. Guess what? Oxygens match. So you can start low and continue to up it if it's not working out for you. Now the next one, this one is probably a little bit easier. And you see here with the HCl, since those are 1-to-1 standalone ones, you can kind of balance those at the end. I would start with the antimonies and the sulfurs. So here I put a 2 in front of the antimony. I put a 3 in front of the sulfur. Oh, hey, look at what it does there. That's 2 times 3, so that's 6 for the chlorine. 3 times 2, that's 6 for the hydrogen. Works out nicely. All I need is a 6 there. Combustion. Okay, butane here. So, start with the C, put a 4. Figure out the H. This is a 5. We'll add them up. So this is 8 plus 5. That's 13. Divide by 2, 6.5. Put the 6.5 here. Okay. And then all we have to do is multiply by 2. And that now easily works itself out. And you can count them if you want to, but it will end up adding up on both sides. Last but not least, the aluminum hydrochloric acid problem down here. This one is a tad bit on the tricky side because you have HCl once again together here as a compound, and you have to look over here. I have 3,2 going on here for the H and the Cl. So I know those are going to have to match. So I'm going to employ the least common multiple idea here. So this is going to need a 3. This one's going to need a 2. So that makes us have 6 chlorines and 6 hydrogens. I can easily put a 6 there. I can easily fix the last aluminums over here because there's 2 in the compound, so you put a 2 there. Some strategies for working some of these, maybe a little bit more complicated. Balancing, I don't know, perhaps maybe you thought they were pretty easy. Alright, so now let's talk about the different types of aqueous reactions. In this particular set of notes, we're going to be concentrating on the precipitation reactions. Later on in Unit 4, there'll be a whole notes, a topic on acid-base, and then there'll be another one on redox. Apparently I can't spell today, but let's try this. Redox, oxidation reduction reactions. So these are to come. These will be later in the unit. We're going to focus on precipitation reactions, which fall under the double replacement grouping of type of reaction. All right, what is a precipitation reaction? A double replacement reaction in which a solid forms and separates from the solution. When ionic compounds dissolve in water, the resulting solution contains separated ions. And this is where that formula writing is going to become necessary because you have to separate them into their ions. And the precipitate, you're gonna have to write that new compound because that stays together and forms the solid. So you're gonna have to write, you know, some new formulas as you're creating your chemical equations. So precipitate, the solid, and the separated ions are all important here for these precipitation reactions. Now we're going to do a lab next week on pivot using the gravimetric analysis idea. Basically what you can do with precipitation reactions, you can filter them and find the mass of the dried product. You find the mass of the dried product, and then you can do the stoichiometry to find anything else in the reaction. What we notice here is, in this particular example, the filtration showing in this picture, you have potassium iodide, that's AQ over here in this beaker. This beaker you have lead to nitrate. In that one, they're both clear solutions by themselves, but when you put them together, you start to see the bright yellow precipitate form, and it falls to the bottom. Well, what is that bright yellow precipitate? It's lead to iodide solid, okay? So, and you see it forming a nice crystalline pattern at the bottom of the diagram there. This is what we're going to be talking about for those precipitation reactions. Now, we're just going to look at the animation. I'm going to talk you through the animation as to what you're going to see happening here. This will help you with your particulate model diagram drawing. So on the previous screen, you might have noticed that the silver chloride is a white precipitate. That's what we saw in the picture. So we're going to now look at it from an animation standpoint. Sodium chloride plus silver nitrate. They're in these separated beakers, showing you the separated beakers here. The water molecules are being removed so that you can see it better. And you can see over here on this side, hold on, it's going to show you that the big green circles are the chlorides over here. The red circles on the left are the sodium ions. On the right, you see the purple that are the silvers, the silver cation ions, and you see the nitrates, which are the ones that have the 4 atoms attached to each other. Okay? Now what you should notice as we're going through this, the conductivity is very high because they're all separated into ions, so this is like a strong electrolyte being able to conduct electricity. But as they run into each other in the solution, you can see the ionic bond forming between the silver and the chloride, and it's building a lattice structure. It's alternating positives and negatives, and that's what's falling to the bottom. And here it shows you the white powder that is falling to the bottom, which would be the alternating silver plus, chloride minus. All right, we'll finish up with definitions of soluble and insoluble. Soluble, of course, means it dissolves in the water, in the solution. When it's dissolved, we write AQ next to it in the chemical reaction. If it is insoluble or precipitates out, the solid's going to form, or it's just not going to dissolve. Like I could put powdered silver chloride in water all day and it's just not going to dissolve. But if you combine one that has silver in it and one that has chloride together, it's also going to form the white powder. But you would write the parentheses S next to the ones that's precipitating out. Also up here, the diagram does a nice job of representing the animation as well, except for the differences. Instead of sodium, you have potassium, but it's also a group 1 alkali metal. But it basically does the same thing. You form the lattice crystalline structure at the bottom, that's the precipitate powder, and you are left with the K+ ions and the NO3 ions floating around in water. Now later on, we'll identify those ones that don't react as spectator ions. So you'll get familiar with that, and then we will proceed with writing out the Net Ionic Equations.